Welcome. Have you ever wondered how a computer can beat a chess grandmaster? Well, the secret is something called adversarial search. In this explainer, we're going to break down the exact AI strategies that transform these machines into master tacticians, not just in games, but in pretty much any competitive scenario you can think of.
Okay, so here's our game plan. First, we'll get the lay of the land, the competitive environment. Then, we'll see how an AI literally maps out a game. After that, we'll dive into a core strategy called Minimax, see why it kinda needs a speed boost, and then uncover the really elegant trick that makes it all work in the real world.
First things first, we really need to understand the battlefield itself, the specific kind of environment where these AIs have to operate and compete.
So, we're talking about situations when you've got more than one agent or player. And here's the key, their goals are in direct conflict. They're all hunting for a solution in the same space, but only one of them can actually win.
And that's the formal term for it right there, adversarial search. The easiest way to think about it is any classic game, like chess or even something as simple as tic-tac-toe. Every single move you make is to better your own position, but at the same time, your opponent is doing everything they can to counter you and win for themselves. Now, what I think is so cool about this slide is how it neatly categorizes all these different games. So on one axis, you've got information. Is it perfect, like in chess, where you can see the entire board? Or is it imperfect, where some info is hidden, like in poker? And then, on the other axis, you've got predictability. Is the game deterministic, with zero random chance? Or is it non-deterministic, with things like dice rolls or shuffled cards?
For the rest of our discussion, we're going to zoom in on a very specific type of game, the zero-sum game. This is pure competition, plain and simple. One player's goal is to maximize their score, while their opponent's only goal is to minimize that exact same score. If I win, you lose. That's it.
So, how in the world does an AI even start to think about what moves to make in this kind of high-stakes environment? Well, it starts by drawing a map, a very, very big map.
And this map is what we call a game tree. Every single point or node in this tree represents a specific state of the game, like a snapshot of the board. And every line or edge that connects these nodes represents one legal move a player can make from that state.
And this tic-tac-toe example just perfectly illustrates the whole idea. The root at the very top, that's the empty board. The next level down shows all the possible first moves for player X. The level below that, all of O's possible replies. And it keeps going like that until you hit the bottom. These are the terminal states where the game is over. Each one gets a score, or a utility value, +1 for a win, 0 for a draw, and -1 for a loss.
Okay, so now that we have our map of every possible future, how do we actually find the best path to victory? Well, that brings us to our first big strategy for navigating this game tree.
It's called the Minimax algorithm, and it's all built on the assumption that both players are perfectly rational. We call them Max and Min. Max, which is our AI, will always choose the move that leads to the best possible score for it. And it works under the assumption that Min, its opponent, will always choose the move that leads to the worst possible score for Max.
The whole process is really methodical. First, the algorithm explores the entire game tree, going all the way down to the end of every single possible game. Then, it starts working its way back up. At each level where it's Min's turn, it'll pick the move with the lowest value. And at each level where it's Max's turn, it'll pick the move with the highest value, pushing that choice up the tree.
Let's just trace this example. It makes it super clear. Look at the very bottom layer. Those are the final scores. Now go one level up. The maximizer looks at its options and will always pick the best one. So a 4 from its first set of choices and a 7 from its second. Now go up one more level. It's the minimizer's turn. It looks at those results and picks the worst possible outcome for Max. So from B, it chooses 4, and from C, it chooses -3. Finally, at the very top, Max looks at its two options, 4 and -3, and makes the optimal choice, the move that leads to a guaranteed score of at least 4.
So Minimax is guaranteed to find the absolute best move. But, and this is a huge but, there's a major catch. It's a brute force approach. And for any game that's even a little bit complex, that becomes a massive problem.
So you can see here, Minimax has some really great properties. It's complete, meaning it'll always find an answer. And it's optimal, as long as your opponent is also playing perfectly. But look at that time complexity. That's the killer. It's O of B to the power of D, where B is how many moves you can make each turn, and D is how many turns deep you're looking. For any complex game, that number just explodes.
And I'm not exaggerating here. For a game like chess, with its huge number of possible moves and deep game trees, it is physically impossible to search every state. So that leads to a huge question. How can we get the perfect rationality of minimax without, waiting for the heat death of the universe to get an answer?
Well, the answer is pretty elegant. You have to work smarter, not harder. We need a way to just ignore entire sections of a game tree that are obviously bad ideas without having to waste time exploring them.
And this is where it gets really, really clever. The technique is called alpha-beta pruning. It's a brilliant optimization that gives you the exact same result as minimax, but it does it by intelligently cutting off, or pruning, entire branches of the search tree that it knows for a fact cannot possibly affect the final decision.
So the magic here is that it keeps track of two values as it searches, alpha and beta. Alpha is basically the best score that max is already guaranteed to get somewhere else in the tree. And beta is the best score that min is already guaranteed. And if, while it's exploring some new branch, it finds that the potential score for max is already better than what min would ever allow, it just stops. It prunes the branch. There's literally no point in looking any further because a smart opponent would never let you go down that path anyway. This slide just captures the power of this idea perfectly. You can see the concept of the full, massive tree on the left, and then the much, much simpler pruned version on the right, with all the useless branches just chopped off. It gets to the exact same answer, but it does it by looking at way, way fewer states. This is a huge, game-changing boost in efficiency. All right, let's wrap this up and quickly review the core winning strategy we've just unpacked for creating a seriously smart AI. So, we started by framing the problem as an adversarial search. Then, we used the minimax algorithm to find the theoretically perfect move by mapping out every single possibility. And finally, we made that whole process practical for the real world by optimizing it with alpha-beta pruning. And remember, these ideas aren't just for playing board games. They really are the fundamental logic behind any AI system that needs to make smart choices in a competitive environment. We're talking everything from automated stock trading to military strategy simulations. Understanding minimax and alpha-beta pruning is absolutely key to understanding how modern AI makes strategic decisions against an intelligent adversary.